Hey Pre-Cal, today we're going to work on solving more trigonometric equations. If you look at this first one, you'll notice it has both sine and cosine. If I were to try to get everything on one side, which I'm probably going to do, it still might be tricky because again I have a sine and cosine, but I don't have a GCF. So notice right up here it says that sometimes it's helpful if you only use one trigonometric function, and this is what brings us back to those Pythagorean identities. So what I'm going to do to start us off is I am going to substitute in place of cosine squared x 1 minus sine squared x. Again, this comes from that first Pythagorean identity that we learned that said sine x squared plus cosine x squared equals 1. So those identities are coming back. Don't forget them. Sometimes we need them. So I'm going to go ahead and distribute the 2 to that. So I have 2 minus 2 times sine squared x. So I'm going to take everything over here on the right. I'm going to move it over to the left. I'm going to move the 2 over using subtraction. I'm going to move the sine squareds over using addition. And then as I write over here on the left hand side, I'm also going to put it in descending order. So I'm going to start with the sine squared x and then the sine x and then the constant. So I've got 2 sine squared x. I'm going to put that plus sine x. And then at the back is where I'm going to combine that 1 minus 2, and 1 minus 2 is negative 1. And now my other side is equal to 0. So remember I showed you guys yesterday that sometimes we have to factor. Looks like we're going to have to factor this. Now some of you might prefer to look at this problem for just a moment as, let's say, 2w squared plus, I'm writing the wrong thing, plus w minus 1 equals 0. Again, all I did right there was in place of sine x, I changed it to w, because that might help you be able to see that you need to do a sum and product chart. So if I were doing a sum and product chart, my sum is 1, my product is negative 2, and the numbers that would work would be a positive 2 and a negative 1, and I'm going to put them both over the leading coefficient of 2, and 2 over 2 reduces to 1 over 1. So this would be, if I were factoring it this way, it would be w plus 1 and 2w minus 1, but I'm going to get rid of that, and no longer am I going to use the w. I'm going to come back over here and change that to sine x plus 1 and 2 sine x minus 1. Now, if you're comfortable with just factoring it from here to here without writing it like this, that's fine. You don't have to show your work for this. If you feel comfortable without having to set the sine x or whatever that trig function is to a variable, you don't have to do that. You can just write it like this. That's fine. All right, so now I'm going to take each of those factors, the sine x plus 1 and the 2 sine x minus 1, and I'm going to set them both equal to 0. So the first one, I'm going to get sine x equals negative 1. The second one, after I add 1 and then divide by 2, I'm going to get sine x equals 1/2. And here's where I need to remember about the unit circle. So let's think unit circle, or even you can think the graph of sine. I really like to think the graph of sine a lot of times. Remember, sine is the wave. When does the wave hit a y value of negative 1? Right here is where we get that y value of negative 1. That occurs at 3 pi over 2, if you remember back to what the graph of sine looks like. And then it doesn't occur again until it goes around the circle a whole other time and continues that way. So I'm going to say that my answer for that is 3 pi over 2 plus 2 pi k. That's going to be one of the solutions for this problem. So I'm saying that it occurs at 3 pi over 2, and then every time I go back around the circle, however many times I decide to go around, it occurs again. Now over here, I want to find out where sine x is equal to 1/2. So first, let me just figure out, well, what quadrants would that be possible in? That's going to be possible to have a positive 1/2 in quadrant 1 and in quadrant 2 because sine is also positive there. So this is where I need to go back and think of my unit circle. I hope that you guys are feeling more comfortable with the unit circle because I would like to have to draw it less in these notes than I did in yesterday's notes. If you're struggling, you might want to pull a unit circle out so that you can look at it, but just keep in mind when you go to take the test, you might have to recreate that unit circle, but you won't be able to just bring a unit circle with you. You have to know the unit circle. So where would this occur? Well, in quadrant 1, when I get a y value of 1/2, that's when my radian measure is pi over 6. And in quadrant 2, that occurs at 5 pi over 6. So the way that I'm going to write these answers is pi over 6 plus 2 pi k. Again, I'm saying this occurs in quadrant 1, and then I can keep going back to quadrant 1 over and over again as I go around the circle multiple times. Same thing is going to happen for my quadrant 2 answer. So I end up with 3 different values that will work for number 1. All right, let's take a look at number 2. So number 2 also has both sines and cosines. Here's what I want you to notice that's different, is this one is a 2x and this one is a 1x. And so that means that I need to think about my double angle formulas that we learned, I think it was part 1 of section 7.3. Sine of 2x, there was only one formula for that, and that was 2 sine x cosine x. So I'm going to use my double angle formula and replace the sine of 2x with 2 sine x cosine x. And then I still have the minus cosine x behind it. All right, now in the last problem, we got it to where we had just a single trig function. We did nothing but sines. But in this particular problem, you may notice that we actually have a GCF. So why don't we take that GCF out and see if that's going to help us out. So when we divide by cosine x, we get 2 sine x minus 1. That looks pretty good because now I have 2 factors, and those factors each have their own trig function. So I'm going to set that cosine x equal to 0, and I'm going to set the 2 sine x minus 1 equal to 0. I'm going to start over here with this one because it looks really familiar because we just did the same exact thing right above it, right there. We already knew that we were going to have a quadrant 1, quadrant 2 answer. There's no point in me doing this work all over again. Let's just write down what that answer was. So we have our quadrant 1 answer, and we have our quadrant 2 answer right here. Now let's come over here and talk about cosine. Cosine being 0. Well, again, you can go back to the unit circle, but in my mind, when I get values of either 0, 1, or -1, to me it's just easier to remember the graph. And remember, cosine is the wave, right? I'm not the wave. The valley. Sorry, y'all. The wave was sine. The valley is cosine, and it is going to give us a y value right there and right there. And if you guys remember, we have a pi over 2 and a 3 pi over 2. And then it would continue, right? Because it would come back down at 5 pi over 2 and a 7 pi over 2, on and on. So for this one, we've got pi over 2, but how long does it take it to get to the next one? Do I have to add 2 pi k? Nope, because this is only a distance of 1 pi. To get from pi over 2 to 3 pi over 2, you would have to add 2 pi over 2, which reduces to pi. So I'm going to add plus pi k, multiples of pi for this one. So there are my answers for example number 2. So again, knowing the unit circle is super important. If you can remember the graphs of sine and cosine, sometimes that really helps out too. And you also need to know all these formulas we've been learning in this chapter. All right, example 3, a little bit different for a couple of reasons. One is just the directions are different. This time, it doesn't say to solve for all of the solutions. It gives us a very specific domain. It says we're going to start at 0 and we're going to go until we get to 2 pi, but we don't get to include the 2 pi. So in other words, all of your answers are going to be answers as if you were going around the circle just one time. You cannot go multiples of that. They just want you to go around just one time, and that's where your answers are going to be. Now, we were also given a hint here, and I'll tell you why. here we have cosine x plus 1 equals sine x. You have two different trig functions. There's no GCF, so I can't factor anything out. And not only that, but I can't change cosine x into sine x or vice versa. If I were using the Pythagorean identities, that's a cosine squared x or a sine squared x. And so neither of these have that square to it. So that's why they give us a hint. It says square both sides, but it also says that, hey, if you're gonna square both sides at the end of this problem, you're gonna have to check for extraneous solutions. So here we go. We are gonna square both sides. Now guess what that means, y'all? That means over here, we have to FOIL, because what does that mean? That means that you have cosine x plus 1 and you're multiplying it times itself, cosine x plus 1. On the other side, I just have sine squared x. So let's FOIL together. First, I would get cosine squared x. Outer, I would get cosine x. Inner, I would also get cosine x. So I'm gonna go ahead and combine like terms, and now I have 2 cosine x. And then for last, I'm gonna have 1. Now on the other side, I have sine squared x. But what do we know about sine squared x? Well, going back to that Pythagorean identity of sine squared x plus cosine squared x equals 1. If I were to solve for sine squared x, I would get 1 minus cosine squared x. So let's do that, because then that way all we're dealing with now are cosines. All right, now clearly I have quadratic, right? With these trig functions, because it's being squared. So I'm gonna take everything over here on the right, I'm gonna move it over to the left. So I'm gonna subtract the 1, and then I'm going to add the cosine squared x. So let's see what we've got. I have 2 cosine squared x plus 2 cosine x. The 1 and the minus 1, they're gonna cancel each other out. And then we have 0. So I've got a GCF. They both have a 2 and they both have at least 1 cosine x. So when I take that out, I'm gonna be left with cosine x plus 1. So now I can take, oh, my pencil's doing something funny. Why? Hold on. Lead issues. All right, so I have 2 cosine x equals 0, and I have cosine x plus 1 equals 0. So over here, I would divide both sides by 2, which would give me cosine x equals 0. Over here, I would subtract by 1, and I would get cosine x equals negative 1. All right, I think I'm gonna go back to cosine and remember what that looks like. So cosine is the valley. Let's talk about where does it equal 0. It equals 0 right here, and it equals 0 right here. Now remember on this one, we have a very specific domain. So we will not add a pi k or a 2 pi k because we can only be from 0 to 2 pi. So we have this one right here, which is at pi over 2. We have this one right here, which is at 3 pi over 2. Now if I come over here, where do I get a y value in my cosine graph? That's at negative 1. Well, that occurs right here, and that's when x is pi. So I have 3 answers, but remember, it said that we have to check, because sometimes when you square both sides, that might make one of those extraneous. So I'm gonna check. Let's start with pi over 2. So I'm gonna go to the original problem. Cosine of pi over 2 plus 1 equals, does it, we're trying to figure that out, sine of pi over 2. So again, you're going back to the original problem before we squared both sides. Okay, so cosine of pi over 2 is 0. And then sine of pi over 2 is 1. Does 0 plus 1 equals 1? Absolutely. Now let's check the 3 pi over 2. So again, just going back to that original problem, and we're plugging it in. All right, so cosine of 3 pi over 2 is 0. And sine of 3 pi over 2 is negative 1. Does 0 plus 1 equal negative 1? No way. So that is not going to be one of our solutions. Now let's check the last one. So we're going to do cosine of pi plus 1. Does it equal, oh, I'm writing the wrong thing. Does it equal sine of pi? All right, cosine of pi is -1. Sine of pi is 0. Does -1 plus 1 equal 0? Yes. So for our answers, we are just getting the pi over 2 and the pi. Those are the two in our domain that work. All right, so here it says when solving trigonometric equations that involve functions of multiples of angles, first we solve for the multiple of the angle and then we divide to solve for the angle. That's very wordy. Let me just walk you through this and make this as simple as possible. Again, notice our directions give us a very specific domain, so we're just going to be going around this circle just one time. Notice it says 2 sine of 3x, that is a multiple of an angle, because remember x represents the angle, minus 1 equals 0. I'm just going to start by trying to get sine of 3x by itself. So how do I do that? Easy. I add the 1, I divide by 2. So right now I have sine of 3x equals 1/2. Now if that 3 is throwing you off, what you can do is use substitution and say, hey, I'm going to replace the 3x with a theta. So let's pretend for a second that we have sine of theta equals 1/2. So our minds need to be thinking about where would this occur, okay? Does that make sense? So we could get quadrant 1 and quadrant 2. That's where sine would be a positive value. Now where exactly would that occur? Well, in quadrant 1, sine is 1/2 at pi over 6. That's our quadrant 1 answer. And in quadrant 2, our answer would be 5 pi over 6. I hope everybody's following me. So this right here, this is a quadrant 1 answer. This right here is a quadrant 2 answer. Now, I know we have a specific domain, but pretend with me for just a moment that that direction wasn't there. What would you do? Well, if I wanted to get back to quadrant 1 over and over again, I would put plus 2 pi k. And I would do the same thing if I wanted to get back to quadrant 2 over and over again. I would add plus 2 pi k. So here's what I have currently. Now this is not my final answer, but I have a quadrant 1 solution, I have a quadrant 2 solution, and I have what it takes to continue getting back there. But the reason that I'm not done is that in our problem, we actually don't have theta, do we? We replaced the theta, or we put the theta in place of 3x. So I'm gonna come over here and get rid of the theta and now say 3x equals pi over 6 plus 2 pi k, and 3x equals the other solution of 5 pi over 6 plus 2 pi k. Because in our problem, we didn't have theta, we had x. So we now need to solve for x. Does that make sense? So I'm taking the theta out, I'm replacing it again with the 3x, which is what we originally started with. So now I've got to solve for x. Well, how do I get x by itself? I divide by 3, which is the same thing as multiplying by a third, right? So that's what I'm gonna do because I already have fractions on the other side. But here's what I want you to notice. When you do that, you have to multiply both of those things by a third. So let me show you what that looks like. If I multiply pi over 6 times 1/3, that turns into pi over 18. Remember, you're gonna multiply straight across. Numerator times numerator, denominator times denominator. The same thing is going to happen with the 2 pi k. Right now that's over 1, and I'm going to multiply it times 1/3, and I'm going to get 2 pi k over 3. Does that make sense? Multiplied straight across, top times top, bottom times bottom. I'm going to do the same thing over here. Again, I would multiply both sides by a third. So when I do it to the left, that makes the 3 go away. Over here, I have to distribute this, right? So 5 pi over 6 times a third turns into 5 pi over 18. And then I have 2 pi k over 1 that I'm going to multiply times a third, and that turns into 2 pi k over 3. All right, our answers are looking pretty good. but we have to go back to those directions that said that we only want answers between 0 and 2 pi. So here we go. I need y'all to pay attention with me, okay? I'm going to start with this first one right here. So my first answer is pi over 18. That's my first solution. Now, if k were 1, meaning I'm just remember, k represents how many times are you deciding to go around. So it's an integer, right? If k were 1, then I would be taking this pi over 18 and I would be adding it to 2 pi over 3. Remember, I'm assuming that k is 1. Well, if I'm going to add those together, I need a common denominator. So 2 pi over 3 is going to turn into 12 pi over 18. So pi over 18 plus 12 pi over 18 is 13 pi over 18. All right, let's try that again. Again, I'm going to start with my pi over 18, but this time I'm going to say, okay, what if k is 2? If k is 2, then 2 pi times 2 is 4 pi. So I'm going to have 4 pi over 3. But again, remember, I need a common denominator. So I'm going to turn that into 24 pi over 18. So pi over 18 plus 24 pi over 18 is 25 pi over 18. All right, let's do it again. Pi over 18. This time I'm going to say, okay, what if k is 3? Well, if k is 3, then 2 pi times 3 is 6 pi. So I have 6 pi over 3. Again, I need a common denominator, don't I? So I'm going to turn that into a 36 pi over 18. So pi over 18 plus 36 pi over 18 is 37 pi over 18. Now you might be asking yourself, oh my gosh, how many times, Miss Wingard, are we going to do this? I'm so glad you asked. Let's talk about this for a second. We said that we were going to go from 0 to 2 pi. Well, if you look at this last one right here, if you were to break that down into a mixed number, I'm just going to come over here because I'm running out of space. If I had 37 pi over 18, well, 18 goes into 37 2 whole times with 1 left over. So that turns into 2 1/18 pi, which is too big. So that's when I know to stop. Does that make sense? In other words, if you want, you can change this 2 pi to 36 pi over 18, right? This would reduce to this. So once I get to this or higher, I'm not allowed to include it. So far I have these 3 answers, but now I have to do it for this one as well. Y'all ready? Here we go. So we have 5 pi over 18 as our first one. So I'm going to take my 5 pi over 18. And again, I'm going to say, okay, well, what if k is 1? Well, I've already done all that work over here, so let's use the work we've already done. You want to work smarter, not harder. We changed that 2 pi over 3 to 12 pi over 18. And when we add those together, we get 17 pi over 18. So far, so good. Now we're going to say, okay, what if we take that 5 pi over 18 and we put a 2 in for the k, which is what we did right here a minute ago. So let's reuse that work. So we turn that into 24 pi over 18. And when you add that to the 5 pi over 18, we now have 29 pi over 18. And if we do it again, and again, I'm going to reuse the work I've already done over here. So I'm going to add that to 36 pi over 18. What happens? It's going to be too big. So these 3 are going to be the answers from that one. So when I go to write my answer, I'm just going to write them in order from least to greatest. I have pi over 18, right? Then I have 5 pi over 18. Then I have 13 pi over 18. Then I have 17 pi over 18. Next is 25 pi over 18. and the last one is 29 pi over 18, and all of those fall within our domain of being between 0 and 2 pi. So really, I don't think the pre-cal part is the difficult part to this problem. It's the algebra part that you need to pay attention to, where you're using substitution and then you're having fractions and you're having to come up with common denominators. So you want to be careful with the algebra. I don't think the pre-cal part is hard. I think it's the algebra that might get a couple of you. All right, let's take a look at the next one. So again, the directions are the same. We have a very specific domain. First thing I'm going to do is try to get tangent of x over 2 by itself. How do I do that? I'm going to add 1, and then I'm going to divide by the square root of 3, and that gives me 1 over the square root of 3, which if you want, let's rationalize that. Let's turn that into the square root of 3 over 3. Now notice here, again, you don't have just a regular x. So what I'm going to do real quick is I'm going to replace the x over 2 with a theta. So if I had tangent of theta equals the square root of 3 over 3. Well, where could I be? I could be in quadrant 1 because everything's positive in quadrant 1. I could also be in quadrant 3 because tangent is positive in quadrant 3. So where does that occur? Well, in the unit circle, the quadrant 1 answer is going to be pi over 6. Now, what would the quadrant 3 answer be? Well, here's what I want you to remember. If you're in quadrant 1, to get from quadrant 1 to the quadrant 3 answer, you have to go 180 degrees. So rather than having a whole separate answer, let's just put plus pi k. That's what we did yesterday, right? If we had a quadrant 1 answer and we also needed a quadrant 3 answer, we were able to add pi k because we were going 180 degrees. So now I'm going to replace the theta with the x over 2. And the goal here is we need to get x by itself. And how do we do that? We're going to multiply both sides by 2. And that means, again, we have to distribute, okay? So if I distribute pi over 6 times 2, that's 2 pi over 6, which reduces to pi over 3. And then I'm going to distribute the 2 to the pi k, and that turns into 2 pi k. Now remember, our directions are very specific, that we want to have an answer between 0 and 2 pi. So obviously my first answer is pi over 3. What's going to happen if I add multiples of 2 pi to it? Well, already that's going to be too big because I'm not allowed to be over 2 pi. So this is, for this problem, the one and only answer for example number 5. All right, example 6, this one we want to find all the solutions. So this means that you'll be able to leave your answer with a plus pi k or a plus 2 pi k or something along those lines. We don't have to find the specific ones. Here we have sine of 2x equals 2 times tangent of 2x. Well, let's talk about what we know. This clearly we have multiples, right? This is a 2x and this is also a 2x, but what do you guys remember about tangent? I'll tell you what I remember. I remember that tangent is sine over cosine, but since it's not just an x, it's going to be sine of 2x over cosine of 2x. So at this point, what could you do? Well, what if we multiply both sides by cosine of 2x? So I over here have cosine 2x times sine of 2x equals, on the other side, we have 2 times sine of 2x. All right, not bad. No longer do we have a fraction. Might be helpful to get everything on one side. I'm going to move this over here using subtraction. So I'm going to have cosine 2x sine 2x minus 2 sine of 2x equals 0. Important to note, you could have moved this over here if you wanted. I just chose to move it all over to the other side. And I noticed that we have a GCF, because look what we have in both of them. We have a sine of 2x, so let's take it out. So when we take that out, we're left with cosine 2x minus 2. So at this point, we're going to set each factor equal to 0. This one's already set equal to 0. That's great. This one over here, I'm going to add the 2 and get 2. Now again, what we did in the last couple of problems was we took out this and we replaced it with a theta, and you're welcome to do that. Some of you though are going to feel comfortable with just continuing to solve, and here's what I mean. So when I solve this, I'm going to have 2x equals blah blah blah, and then after I solve it using my unit circle knowledge, then I would continue to use algebra and get x by itself. So that's what I'm going to try. Now let's think about sine. I like to go back to the graph because the graph's pretty easy. Remember, it's the wave. Where do you get values that y equals 0? Right here, right here, right here. 0, pi, 2 pi. And it would continue, right, to go backwards too. It would go to negative pi, negative 2 pi, negative 3 pi. So those are all multiples of pi, right? So I'm just going to write pi k. But notice I'm not just going to write a 2x. I'm not just going to write an x. I'm going to write 2x because that's what this is. Does that make sense? So we found out where all of our values of y were 0. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, all multiples of pi. But now I have to go one step further because I have to get x by itself. And so I'm going to get that x is pi over 2 times k. Now let's come over here and take a look at what we have. We have cosine of 2x equals 2. So I could either think about my unit circle, or I'm going to go back to the graph of cosine because I know that cosine is the valley. Now remember, the valley, it goes up to 1, it goes down to negative 1. When does it get a y value of 2? Never, because it doesn't go higher than 1 and it doesn't go lower than negative 1. So that part can't be done, which tells me that the only answer that we're going to have is pi over 2 times k. All right, example 7. Again, we're finding all of the solutions, but we're in a very specific interval here. So first thing I'm going to do is divide both sides by 3. And I don't particularly like working with cosecant because I feel more comfortable with its reciprocal, which is sine. So I'm going to turn this real quick. Oh, I forgot no, I didn't. I'm going to turn this into 1 over sine squared x. Oh, you know what would be easier, y'all? Miss Wingard needs to use her brain. If you turn this into sine squared x, then we'll take the 4/3 and change it into the reciprocal. Duh, because they're reciprocals of one another. That looks so much nicer, doesn't it? All right, now how do I get just a sine x? Well, I have to square root both sides, don't we? And when you square root both sides, what do you include? You include plus or minus. All right, well, 3 is not a perfect square, but 4 is. So we get to take out a 2. So we're going to have answers in all 4 quadrants because sine could be positive in quadrant 1 and quadrant 2. Sine could be negative in quadrant 3 and quadrant 4. So we need to have answers for all 4 quadrants. So let's think about quadrant number 1. Where do we get a y value of the square root of 3 over 2? That occurs at pi over 3. All right, quadrant number 2 is also where sine would be positive. Where do we get a y value of the square root of 3 over 2? That's at 2 pi over 3. Now once we get to quadrants 3 and 4, that square root of 3 over 2 turns into negative because the y values go down. And where does that occur in quadrant 3? It occurs at 4 pi over 3. And where does it occur in quadrant 4? It occurs at 5 pi over 3. And that's going to be all of the answers that we use because we had a very specific domain from 0 to 2 pi. So that one I think was pretty easy. All right, so let's take a look at number 8. We're going to find all solutions. Again, we have a specific domain, so we're just going to be in that circle just one time. We have lots of different trig functions, which can be overwhelming. So why don't we try to change everything to sines and cosines? That might be the easiest. So I'm going to change this to 1 over cosine x times sine x over cosine x minus cosine x times cotangent is the reciprocal of tangent. So this is going to be cosine x minus sine x, and then it's equal to sine x. So far I've just changed everything to sines and cosines. So let's see what we have. The first fraction, we have sine x over cosine squared x. Then we have minus cosine squared x over sine x. And then the other side, we don't have a fraction at all. Okay, so remember, one thing you can do if you want to get rid of fractions is you multiply both sides by the common denominator. What would the common denominator be? Well, we need a cosine squared x, and we also need a sine x. So I'm going to multiply both sides by that value. All right, so I have to distribute over here, right? I have to take it to the first fraction as well as to the second fraction. So let's see what would happen if I multiply this times this. One thing I know is the cosine squared x is going to cancel out. That's going to leave me with sine x times sine x, which is sine squared x. So that takes care of my first fraction. Now let's look at the second fraction. The sine x and the sine x are going to cancel each other out. I'm going to be left with cosine squared x times cosine squared x, which turns into cosine to the fourth x. On the other side, I'm going to multiply those together, and I have cosine squared x times sine squared x, or maybe you wrote the sine squared x in front. Doesn't matter, either one is good. So here's what I noticed. I noticed that we have sines and cosines. This looks kind of like a difficult problem. What if we change them all so that they're one or the other? I'm going to change the signs because this one, see how it has a different exponent? So what if I get rid of the sine squared x? Because what do we know about sine squared x? We know that it is the same as 1 minus cosine squared x. And again, that just comes back from the Pythagorean identity, right? So I'm just replacing those sine squared x's with 1 minus cosine squared x. So over here, I have 1 minus cosine squared x minus cosine to the fourth x. The other side, because that's multiplication, I'm going to distribute. So I get cosine squared x minus cosine to the fourth x. Okay, so we probably need to move everything over. I'm going to take these, move them over here. So I'm going to subtract cosine squared x. I'm going to add cosine to the fourth x. Ooh, I like this. What's going to happen to those cosine to the fourth x's? They're opposites. They're going to cancel out. I'm going to combine like terms. I'm left with 1 minus 2 cosine squared x equals 0. This looks now like a much easier problem, doesn't it? So I need to get everything away from the cosine squared x. So how do I do that? Well, I would subtract the 1 over here. So now I have negative 1, and then I would divide by negative 2. So that turns into a positive 1/2. But I don't want cosine squared x. I want cosine x. So I'm going to square root both sides, which means I need to include plus or minus. So 1 is a perfect square, 2 is not. Might be helpful to rationalize that. That turns into the square root of 2 over 2. So now we're at the part of the problem that I think is probably the easiest. We're going to have answers in all 4 quadrants because cosine is positive in quadrant 1 and 4, and it's negative in quadrants 2 and 3. So we're going to have an answer for each quadrant. So let's think back to the unit circle. In quadrant 1, cosine would be positive, and it would be a positive square root of 2 over 2 at pi over 4. In quadrant 2, cosine would be negative, and that occurs at 3 pi over 4. In quadrant 3, cosine would also be negative, and where does that occur? That occurs at 5 pi over 4. And lastly, in quadrant 4, it would be positive, and that occurs at 7 pi over 4. So the knowledge of the unit circle is going to help you greatly, or if you didn't learn it, hurt you greatly in this section. All right, so what I would encourage you to do is try example 9 and 10, just try it, and then I'm gonna do another video where I pick up with those two examples, okay? So I will talk to you in the next video.